Okay, you can find references in my webpage. There. All right, so in my title of my talk, I mentioned Ranga Dias, and this is from a webpage that just appeared a couple of days ago about his company, Unearthing Materials. And apparently he has left an indelible mark on the field of physics. And the company is right now hiring, and they are claiming to put a dent in the universe. I would like to tell you an alternative story of this. Basically, I believe that Ranga Dias is playing a very important role as a canary mine. And let me remind you what that saying means. It's something that gives an early warning of danger or failure in the way that in the past a canary taken to mine would die. I don't wish that, but it would warn if there is a problem. So this is a mine, and the mine is being mined by people that are basing their mining of high-TC superconductors on BCS theory. So BCS theory told us 70 years ago or something that the interaction between electrons resulting from virtual exchange of phonons is attractive when the energy of the electron states is less than the phonon frequency. And so the theory predicts that the TC is proportional to the mass to the power -1/2. So if you want to raise the TC, which is something that a lot of people would like to do, you want to use light elements, so the mass is small, and especially hydrogen, since the mass is the smallest. So in particular in the US, there has been emphasis in funding work. This is from the National Science Foundation announcement of January 2021 that because of predictions of high temperature superconductivity in hydrogen-rich compounds, there is an effort to do research with the lightest elements and hydrogen in particular to find superconductors at high temperatures, and it's an expanding and active field of research. But I would like to tell you, as I said, that why is it not going anymore? Somebody must be censoring me. That instead, I would like to think that it is an early warning of the. So, every time somebody logs in, I get. Yeah. All right. So the story started long ago, but I will start it with Ashcroft in 2000. He suggested that metallic hydrogen alloyed with some other metals would give the possibility of getting hydrogen very close together, and so you would get high temperature superconductivity due to the hydrogen, but you would need less pressure. You need pressure in order for this to happen. You would need less pressure than if it was pure hydrogen, as he had suggested back in 1968. And so a few years after Ashcroft made this prediction, Eremets and coworkers wrote this paper where they claimed to have found conventional superconductivity at 203 Kelvin, which was higher than any high-TC cuprate in 2015. And they emphasized in the title that this is conventional superconductivity and that it is based on the Berlin-Cooper-Schiffer theory with no theoretical upper bound, etc. So that was 2015. That was the start of this field. And Michael Eremets is a main author here that continued in this work. In fact, his paper was actually motivated by these specific predictions of a year before on metallization of sulfur hydride compounds. And he credits, of course, in his paper that this was the origin of this experimental effort. So, something else happened here. Okay. After that, the next year, no, 2 years later, there was a prediction, again, theoretical prediction in 2017 of high temperature superconductivity in lanthanum and yttrium hydrides. And then 2 years later, there was an experimental paper claiming to find superconductivity in lanthanum superhydride, and then also in the yttrium hydride. So the three papers are confirmation of the prediction of 2012. It was predicted that in calcium hydride high pressure there would be superconductivity, and that took a little bit longer. In 10 years, there were 2 independent experimental verification of superconductivity in calcium hydride. Finally, in early 2020, there were predictions of superconductivity in a compound that had carbon, hydrogen, and sulfur. There were 2 theoretical papers in April and May 2020. And then in October 2020, there was an announcement that this compound with carbon, sulfur, and hydride was in fact a room temperature superconductor. And this is this famous compound that I'm going to be talking about part of my talk called CSH, where Ranga Dias is a key author. And as I say, it was room temperature superconductivity, so people paid a lot of attention. October 14, 2020. So that, there were lots of announcements that superconductivity at room temperature has now been found. Now, why were people so convinced that this was real? Because at the same time, there had been a lot of theoretical, by the way, not only news, but also physicists, like this is a landmark, the result was believable, pretty spectacular, very, very expert physicists were believing that this was true. And the reason everybody believes it is because there had been all this theoretical work. People think that tools are available for accurate predictions of the superconducting critical temperature, that with the sole knowledge of the chemistry, you can predict what the material is going to do. And so all these papers kind of prepare the ground for people to really expect this to happen, and it was found. So anyway, when it came out, so this was the experimental evidence in this CSH compound. Resistance versus temperature showed very sharp drops. AC susceptibility versus temperature showed these sharp drops. Looks like evidence of superconductivity. All right, so immediately when I and my colleague Frank Marsiglio look at it, we decided that this is not superconductivity. So the first thing we pointed out is that the width of these transitions in resistance is very unusual. And the second thing on the susceptibility, I pointed out that there was something that I will tell you in more detail about the susceptibility having to do with Europium metal that raises doubt on the validity of results for this hydride and for Europium. So, all right, so resistance of this material. We pointed out that in regular superconductors, there is some width to the transition, and that width becomes larger when you increase you apply a magnetic field. When you increase the magnetic field, the transition temperature goes down, and the width of the curves increase. And here we are plotting the width versus magnetic field, and they all have a slope. In the hydrides, what you see is that the same graph of width of the transition versus magnetic field is in a lot of hydrides very horizontal. It doesn't change with magnetic field. Here are some examples. I showed you the CSH, and these are other examples of hydride where you apply a magnetic field, the transition shifts, but it doesn't get broader, like in what we call standard superconductor. In addition, the transition width in CSH was very, very, very narrow, and we said that was very unusual. All right, so this was one warning signal that we published in Nature. The other one that took a little bit longer to figure out was the AC magnetic susceptibility. This is the data they showed, and I noticed very shortly, and they say here that these are not raw data that published. The background signal is subtracted from the data, so in fact, what they published, the data is raw data that they didn't show us and background signal that they didn't show us either. There is one graph of raw data here, but everything else is data where this calculation has been made with data that we don't know. And I noticed that there was a paper 12 years earlier in PRL that showed at a very different temperature range, 2 Kelvin versus 170 Kelvin, that showed very similar behavior to the raw data that is actually quite unusual, that the susceptibility in the raw data would drop and immediately thereafter rise is something you do not expect in these measurements. And so I noticed this similarity, and then I decided I really need to look at the raw data and the background. So I requested from the authors of both of these papers the data. Well, it took a very long time to get that information for a variety of reasons. I'm not going to get it. So, yes.
No, maybe most important distinction of conventional type is conductor is changing the heat of water.
Okay.
By the way, maybe
Okay.
You know, now your new superconductors, they are even more high temperature.
Yeah.
So why do you suggest that the physics of water entering vortices and then tends to be events will be similar?
Well, look,
it's not a natural.
I'm saying what they call standard superconductors, which include the cuprates, which include conventional materials, which include magnesium diboride. They may have a lot of differences in maybe the mechanism or this or that, but the distinction between type 1 and type 2 is quite universal. Vortices are quite universal. All these different materials show a broadening of the transition when you apply a magnetic field. And it's kind of follows from general Ginzburg-Landau theory. You don't need to go into very much specific. So I don't know of any way to model a superconductor, the type 2 superconductor, that would not show broadening of the transition when you apply a magnetic field. But we can discuss that later. But as I say, this, well, it's not all that high. I mean, the cuprates are 160 Kelvin, and they show a big broadening of the transition, and these materials are 250 or something. It's a factor of 2. It's not qualitatively different. So, all right, going back to the susceptibility, when I got the raw data, these are the published data for this Europium metal. They showed very nice evidence for superconductivity with this jump in the susceptibility that's independent of pressure in magnitude, which is what you expect. But then when I looked at the raw data, they looked like something totally different that had 2 jumps, and they were like an order of magnitude bigger, which is totally unexpected. And it shows that these jumps are spurious, not related to superconductivity. So published and what was measured contained in the raw data that I received after requesting them were very different, and this resulted in a retraction of this paper a few months later. And I should add that in addition, there was certain features of this, in particular, when I looked at the detailed behavior of the susceptibility in these 2 rectangles, what I found is that when you just take the paper that's published and amplified by 640 times or something, you find that the noise in this and in this, as you can see, is identical. So these are not both measured data, they are copied and pasted from one part to the other. In any event, in the retraction, they say that the susceptibility data were not accurately reported.
But there is of the error in Europium.
No, I'm sorry. This is a published data. What I'm saying is that this structure is noise, okay? And this is...
What is the error of the noise?
It doesn't matter.
Minimum is inside the error or...
It doesn't matter. Well, I cannot tell you. This is what they publish, and the raw data are just numbers, which I plot. All I'm saying is, when you look at this fine structure, that's noise. And you cannot have the same noise at this temperature and this temperature in different measurements, right? That shows that the way that this part was obtained, or alternatively, the way that this part was obtained was that copying and pasting one part into the other part, which is different from what the figure caption says. Yes, that is a shown effect. There is no question about that. Okay? Yes. No, the part of copying here is just that small piece. But then there is a lot of these other differences between published and raw data. So the transformations that were made, taking data, adding a linear function, shifting, all kinds of things. But there's no point in going into detail because all you need to know is that the data did not reflect what was measured. All right. The paper was retracted. Now, why is it relevant? Because there was one author in common in this paper and the CSH paper that did the magnetic susceptibility measure. So based on this, I wrote this paper in mid-2021. I did not have the raw data for the CSH paper yet. I said that perhaps there is a scientific fraud in the CSH paper. Then finally, the raw data were released in December 2021. And I looked at them, and well, that was my conclusion. Now, let me show you, for example. So this is the data that were published in the paper Amplified. The green curve, raw data is the black curve, and background is the red curve. I copied this part of the background and shifted it down here just to show that both in the upper part and the lower part, the noise in the background and in the raw data is very, very similar, and they are supposed to be independent measurements. Okay, so that's one evidence, and you see the noise in the data, which is the difference between two noisy functions, is very much smaller now, which is very anomalous. Also, the data, if you look at them closely, and I will amplify this picture later, has very strange structure that you can see, like this is nearly horizontal, then there is text. You'll see that in a minute. So I'm going to amplify this version later in the next slide. But so at this point, when I saw this, I started looking at this in more detail, and I teamed up with Dirk van der Marel, who also got interested in this, and we wrote several papers together. That's the title of one of them, and these are references to these papers. And so let me show you what the analysis says. So this is a little part of the curve. The data look like this in red, and the authors say that the data are the difference between this noisy function and this noisy function. And what Dirk and I did is we analyzed the same data that you see on the left and right, and we found that you can represent those data by the sum of two functions, Q of t and P of t. Q of t is this series of steps that analytically can be written as 0.16555 times an integer n. And the green curve, P of t, are third order polynomials that I can give you the coefficients, but there's no point. The point is that we can express the same data not by measuring something and another thing and subtracting, but by doing a calculation in the computer of these two functions. Okay? So this was measured in Dias' lab, and this was calculated in our computer with no lab. Okay? So I can also show you numbers. So here are numbers for what they say is the measured voltage, and these are calculated voltage. You see that the first 7 digits are identical, and this is true for 453 points. And our mathematical analysis indicates that with probability larger than 1 minus 10 to the minus 338, some of those data were not measured in the laboratory. Okay? I can tell you exactly. There is one number which is 0.16555. There is 13 polynomials of third order. So you can multiply 13 by a third order polynomial has 4 terms, and then each term has a number of digits, and then you add them all up and you end up with like 100 digits or so. And then you take the experimental evidence, which is 450 points multiplied by 8, and you get 3,000 or 2,500.
It means that I acted that I didn't express correctly. I have one phenomenon. If you say it is a polynomial, you have some coefficients from the very beginning.
Yeah.
How many coefficients do you send for this theory?
No, this is not a theory. I'm modeling this curve. to modeling this curve. Yeah. Yeah, I just told you, it's 13 different polynomials, and each polynomial has 4 numbers. They are defined. Yeah. Yeah.
I'm very sorry, but my experience with experimentally
yes.
tell me that these 4 parameters, I can see any word what I do.
I'm sorry. I have the numerical values for the published data, and those numerical values are given to 8 or 10 significant figures, okay? That's not a curve that I'm fitting. If I can fit 8 significant figures for 450 points, that's 2,500 independent numbers that I can fit with my 100 numbers. That means those numbers were not measured. That's mathematical, okay? All right. So as a result of this, the paper on CSH was retracted by the journal, okay? But the journal didn't acknowledge that the fabrication took place. They just said the processing had been non-standard, and the authors continue to claim they disagree with the retraction. I don't really understand why, but that's the status of this. I have no doubt, and I'm happy to discuss at length with anybody why this, in my mind, is mathematical proof that these data were not measured. Okay. All right. So let's move on. It's taking a little. Now, what happened with Ranga Dias is that in March 2023, he published another paper that also gained a lot of attention, as you can see in all these news articles, about room temperature superconductivity, near room temperature at near ambient pressure, that in lutetium, nitrogen hydride. Yes. Which jump? In the resistance or in the susceptibility? Well, we need to talk about that. I haven't told you that yet. Okay. That's going to come later. I didn't tell you that. I'm covering several different things. One is that the data of Ranga Dias for CSH, their first room temperature superconductor, was a fraud. Next, we're talking about lutetium, hydrogen, nitrogen, which was announced in March 2023, which again gained a lot of attention as a revolutionary. Okay. Now, people that have tried to reproduce this lutetium hydride so far have not succeeded, but it is being claimed that they didn't make the samples right. Now, I looked at the data, and again, there are several peculiarities. This is what they plot as resistance, but they subtract a background RC. Now, in this case, they gave us the raw data. I didn't have to ask them. And they say that the transition is broad because the sample is inhomogeneous, which makes a lot of sense. Now, when you don't subtract the background, you get something that doesn't look like very superconducting. It's just dropping to 2 from 8. The paper doesn't show this. The paper shows this that suggests superconductivity. Then they show another transition that you see is incredibly sharp. It's 1,000 times narrower than this one. So if this is due to inhomogeneity, this tells you that this sample is 1,000 times more homogeneous than that sample. It was manufactured using the same technique. So these are the same data. The width of this transition is in fact 35 times smaller than the width in CSH that we said was already anomalously small. This is simply impossible. That look at the scale here, 294.2, 294.8. It's impossible that a superconducting transition has this width. It's simply not possible. In addition, there are pressure gradients in these high pressure cells that should broaden the transition. So here's another thing about this lutetium hydride that shows it's not a superconductor. They show voltage versus current at a temperature way below TC, and it basically shows no part of supercurrent. When you look at YBCO, very close to TC, you already find that as you cool, 86 degrees versus 90, you find a large region of 0 voltage, and then it takes off. Here, there is no zero. So in any event, I think this unquestionably says that these resistance drops are not due to superconductivity. Okay, so And that's again the canary in the gold mine. So these resistance drops that Ranga Dias shows us, some of them are these extremely short drops that we know cannot be superconductivity. Other ones are a little broader, and you could say, yeah, maybe this is superconductivity. But the point being, you know, the resistance drops in the Dias lab for some reason that is unrelated to superconductivity. And if it's doing it in this one, that's impossible. Maybe it's doing it in those ones. And then maybe in all these other materials where Eremets and all these other people measure resistance drops, perhaps there is also other reasons. The same reason that Dias lab gives you resistance drops may be also giving you resistance drops in all these items. So, I'm sorry?
You cannot say that.
Because?
Because you do not advise the work of the Eremets.
I will.
In the same way.
No, I will. I will. Thank you. All right, there is a lot of experimental evidence that people claim gives you superconductive hydride. Resistance measurements by several people, something called nuclear resonance scattering, an experiment that was done here in France, I think, by Troyan et al. Optical measurements, magnetization measurements, susceptibility measurements. I told you a little bit of that. Flux trapping measurements. And decentral, very recent, all of these are problems. I won't have time to tell you all the problems. All right. So this is the list of papers that we wrote on the hydrides, a long list of analysis, many in collaboration with Frank Marsiglio. And I want to tell you a little bit. You can find the preprints at my website. So I was at a conference in Ischia a week ago or so, where Eremets talked about his work, and he said it has been verified in other laboratories. Well, but you have to look at the details. So, for example, electrical measurements, Eremets says it has been verified by Nakao et al. And by Osman et al. Well, all right, so let's look at resistance measurements. This is from Eremets himself. You can see how inconsistent the data are. So here, the resistance doesn't go to zero, except maybe, no, it doesn't go to zero at any temperature. Here, it seems to go to zero. Here, it goes to zero below 50 Kelvin. So every time he measures, he gets something somewhat different, it seems to me. This is from this other independent measurement. So Nakao, for example, finds that the resistance drops from 15 to 14, and then they subtract this residual resistance, and it looks like it goes to zero, but you need to subtract 80% of it. Osmond, the other one that Eremets quoted, also drops, but doesn't go to zero even at very low temperature. Shimizu, in a recent paper, finds that it seems to drop at a temperature of 15 Kelvin rather than 150 or something. So they are all very inconsistent with each other. And also a lot of these measurements show these very strange oscillations. I don't know if anybody has seen this in other superconductors. I find it very strange that they show these strange oscillations that usually you don't see in superconducting transitions. Now, let me go on. Eremets talk about magnetic susceptibility. So this is a figure from 2015 where he shows magnetic susceptibility that in the zero field cooling has this change, and in field cooling, this looks pretty plausible, but it turns out he did several measurements, and these he did at the same time, but didn't publish until 7 years later. They show very different behavior, as you can see, and only this one looks kind of more consistent with superconductivity, and the size is also very different between the different measurements. So this size on the scale here is actually tiny. So these jumps are much bigger than these. There's a lot of inconsistency in these measurements, and they only show you one measurement. Now, recently in 2022, they showed these results of magnetic moment versus magnetic field that seems to indicate that it's diamagnetic, and then the field starts to penetrate at what would be the lower critical field. In the same figure, they show you this, which is part of a hysteresis loop. And in fact, it's very strange because these curves and the curves here are supposed to be the same measurement on the same sample. And when you put them on the same plot, they look like this. The one on the left is this curve, and the one on the right is this curve. They should be the same. They are very different, so this doesn't make any sense. So we asked the authors to explain. We didn't get a response. And we asked them to supply the raw data, and we didn't get a response. I'm told by Nature Communications that the authors are going to publish a clarification of this graph someday, but this has been already been more than 6 months. So they have published things that are clearly inconsistent with each other. Apparently, they are doing some, they say in a paper, improvement in the background subtraction procedure. We don't know what this is. And let me remind you that Ranga Dias also had some subtraction that they called user-defined background that then ended up in the journal not liking it. So we don't know what the status of this is going to be, but stay tuned. All right. Now, Eremets also talked in his talk last week about magnetic susceptibility measurements that they have been done in China independently. I'd like to talk about this a little bit. These measurements showed that in this paper by Huang et al., very nice drops in magnetic susceptibility versus temperature that seem to show superconducting transition. And Eremets even today is claiming that this is evidence that sulfur hydride is a superconductor. So I decided, since this is also raw data minus background signal, to ask the authors for the raw data and the background signal, and they send them to me. Okay. So I put them in my computer and plotted them. This is what they look like. The background signal is very smooth, as it should be. The raw data show a little kink, and when you subtract this minus that, in my computer, you get this curve that is identical to the one they published. So far so good. It looks like superconductivity. But then I looked at the data more carefully, and I saw that if I take the delta T, which is the difference in temperature within the different points in the curve, since I had the files, I could look at delta T, and I plotted it versus the temperature itself. I found this graph where this is a blue curve that has a kink at this point, and the delta T versus temperature looks like this, and then it jumps to this exactly at the same temperature where they see a kink in the susceptibility, okay? And that tells me that this is clearly an experimental artifact caused by the change in the temperature step. Now, you might think, and I thought first, wait, if this is undergoing a superconducting transition, then the heat capacity is going to jump, and I'm going to maybe have a change in delta T caused by the superconductivity. The problem is that these are very tiny samples, and the thermometer is like 1 centimeter away from the sample, so the volume of the system involved in the temperature changes is like 1,000,000 times bigger than the sample. So any change in the properties of the sample cannot influence this delta T. This delta T is an experimental artifact. And because it's happening exactly at the same point where they see the kink, it's obvious, I think, that the kink is due to a change in delta T and not to any superconductivity of the sample. And if you look at another pressure, this also showed. Again, I looked at the raw data in the background, and again, the jump in delta T is exactly at the same point. Okay? So anyway, this tells me, and I wrote a comment on this paper saying that the sudden changes in temperature increments coinciding with assumed critical temperature is an experimental artifact. And so they imply that the first change in the slope of the susceptibility, that the entropy of superconductivity is a consequence of the same experimental artifact, cannot be taken as evidence for superconductivity. The authors responded that I'm wrong, that our measured data demonstrate that there is no relationship between the superconducting transition signals and those temperature rates. I don't understand how they can say that because, as I say, to 2 decimal places, they happen at the same temperature. So the logic of what they say escapes. All right, let me move on. This is a set of a lot of different magnetic measurements, mainly on hydrides that we analyze. The point is when you look at them independently, it looks like plausible indication of superconductivity. But when you look at the relation between all these measurements, you find that they are totally incompatible with one another. So let me give you, okay, this is something I kind of already talked about, so I'm going to skip it. The size of the transitions look very different, and the zero field jump should be consistent, and it's very different. It's actually was much bigger in 2015 than it is in 2022. Yes. Yeah, I don't know how I'm going to do it. I'll do my best to speed up. Let me show you something else that's interesting. This is zero field cooling and field cooling curves. And you can see that there is no signal in field cooling. Now, they claim that's because of vortex spinning, that it's sometimes hard to see the signal in field cooling. And that is true. But you see the divergence here that you see in these graphs. This is in the samples after heating them. Down here, they also show the graphs in the samples before heating them, where they are not superconducting, because the samples are not superconducting where they are not heated and processed. They show the divergence at the same temperature, basically, as the ones. So they claim this divergence due to superconductivity, and this, when you ask them, they say, well, we don't know where it comes from. It's obvious to me that there is something else going on here that may account for the same divergence as here than here. All right. I probably should go faster, so I'm going to, okay, let me say one thing about this. Nuclear resonance scattering experiment in 2016 was published and claimed to be evidence for superconductivity. I won't go into the details of the experiment except to show that they applied a magnetic field of 0.68 Tesla that they claimed that the sample kept it outside, and that's evidence that it's a superconducting sample. And they show that this happens at low temperature. It doesn't penetrate the sample. They claim this is evidence that it's a hard superconductor with a large critical current. But then in 2022, they plot this, which shows that the magnetic field penetrates the sample when it's only 0.1 Tesla. So 0.1 Tesla field penetrates in 2022. In 2016, a 6 or 7 times bigger field was kept out. And also the behavior that they see here for the magnetization is not expected for a hard superconductor, which should, rather than showing this sharp break, magnetization versus temperature should have a much smoother behavior. If it was an ideal type 2, it would go to 0 at HC2 rather than going to 0 much more rapidly. So let me skip some of this because I want to, no, let me say this one other thing. Trap moment, trap flux was very recently claimed to be evidence for superconductivity, that when you cool, then apply a field, and then you remove the field, they claim that all this moment gets trapped in the superconductor. And again, this is totally inconsistent. For this field, they claim that the field penetrates, and when you remove it, it gets trapped. In this experiment, the same field didn't penetrate. Again, when you look at the two experiments together, they are inconsistent. How can the moment get trapped if the field doesn't penetrate? Other things are wrong with that. Let me skip this because I'm going to run out of time. Let me talk very briefly about this graph that comes from the same paper. They show a hysteresis loop and a magnetization versus field. And it's the same sample, so you can put them together in the same graph. And so this green curve is this one, and this blue curve at the same temperature, 100 Kelvin, is this one here. Now, this makes no sense whatsoever because this is the way it looks like in a regular superconductor. The virgin curve, when you start from 0 and you apply a field, will match the hysteresis loop, will join the hysteresis loop. This curve is very far, in fact, it's going to 0, rather than joining. So this also shows us random graphs. This suggests a hysteresis loop, but it doesn't go together with the magnetization. So, all right. All right. Let me tell you another thing. When you extract, the authors, Eremets and so on, extract penetration depth from their measurements. This is London penetration depth. They claim it's very, very small, like 20 nanometers. And the TC is very high. Now look what we have in all other standard superconductors. When the penetration depth is very small, the TC is very small. Those are elements that are very pure, very low TC. When you go into type 2 materials, the penetration depth gets a lot larger and the TC starts growing. These have very small penetration depth and very large TC. And also when you look at the coherence length, you find in standard superconductors that when the London penetration depth gets large, the coherence length gets small. These materials have very small coherence length and very small penetration depth, according to the analysis of the experiment. Again, totally inconsistent with what we know about superconductors. All right, what's a possible explanation for resistance drops and zero resistance? Eremets tells us he measures zero resistance and that he extracts a resistivity that's 2 orders of magnitude less than for pure copper. Now, they do 4 probe measurements, and the fact is that if you have a homogeneous sample, you can extract the resistivity from measuring in these 2 configurations, but they do not have homogeneous samples. So there's really no way of getting resistivity out of the resistance measurements that they do. And Eremets himself tells you that the samples are contaminated, that they are purely crystallized, they're imperfections, so they are not homogeneous samples. Now, I've been doing some simulations in resistor networks of the following kinds. Here I have metallic and semiconducting resistors. The black ones are semiconducting, and they become more resistive as you lower the temperature. Now look first at these 2 diagrams, and the only difference is this resistor here. If I do a 4 probe measurements, I'm going to get a voltage here that's 0.2 volts, and a voltage here that's 10 to the minus 6 volts. So if I calculate resistance by voltage over current, I will think that this is a superconductor, when in fact all it is, I'm measuring a small voltage because the sample is kind of disconnected. So these 4 probe measurements, and by taking this resistance to grow as you cool, you can get V over I versus temperature that looks very much like what they measure in these experiments. And there is no superconductivity in these graphs. These are just resistors that are becoming more resistive as you cool. And when you do statistics with these resistor networks, you find that for about 10% of them, you find that they look like superconductors, but they are really not. What they should do, and they never do, is measure with different electrode configurations and see what is the different results, and the papers never report them. Now, there's a precedent for all this. Those of you that are old know the famous TTF-TCMQ example, where they claim there were superconducting fluctuations in a quasi one-dimensional system. And then a year or 2 later, it was found that this apparent giant conductivity came from the 4 probe measurements. Due to the small current flowing, it looked like they were being superconducting, they were not. So I'm saying something very similar is happening in this material. You know, this is based on confirmation bias. They select information that supports their views, ignore contra information, and obviously there is this deeply entrenched belief that these materials are BCS specific. So the other thing that those of you that have been in this field for a long time know is that, as Ranga Dias used to emphasize, there have been no predictions of superconductors other than the hydrides. Only in the hydride era, we are being told that one can predict superconductivity. Before that, nobody could predict anything. So people, let me skip this because we are going to run out of time. People are still saying that these design superconductors are real superconductors, that the theory to a high degree of accuracy can predict all these phenomena. This is a compilation of recent predictions I made, predictions over the last 20 years of materials now that are not under pressure. All these predictions in elements and in compounds with light elements, none of them have been found. And all these predictions were done for materials at ambient pressure rather than at high pressure. So predictions at ambient pressure don't work. Predictions at very high pressure for very small samples seem to be working. Well, why should it be easier to predict superconductivity at high pressure rather than predict light element superconductor at ambient pressure? Nobody has told us anything. So if it turns out that hydrides are not superconductors, I would claim that the validity of the electron-phonon interaction as a mechanism for superconductivity in any material should be called into question, because there are no other examples of successful predictions. And if you go back to look at the periodic table, you're going to see that there is no evidence here that Tc has anything to do with ionic mass. For superconducting transition temperatures, high Tc should be here, low Tc should be on the right. It's totally arbitrary. The TC equation from Macmillan tells us that TC depends on other things. In order to get this, we would have to assume that mu star becomes smaller for heavy elements, or that lambda, the electron-phonon couples, increases with m. There's no theory of that. So in the absence of any systematics in lambda mu star, you would expect some systematics in m, ionic mass, if the electron-phonon interaction was playing a role. There is no systematic. On the other hand, if you look at the Hall coefficient, you're going to find that most non-superconductors have negative Hall coefficient, and most superconductors have positive Hall coefficient. And here's in the periodic table, the superconductors are in brown, and the positive Hall coefficient and negative Hall coefficient, you see the strong correlation. So that leads me to what I would like to talk about some other time, the theory of Hall superconductivity, which I've been working on for many years, that says that you need nearly full bands to get superconductivity. And the key is you need carriers with negative effective mass, carriers near the top of the band. Phonons and ionic mass are irrelevant. You need positive Hall coefficient, negatively charged ions, and so on. So as I say, we're working on this for 35 years. I want to tell you in the last 5 minutes a couple of things about this theory. This is a prediction we did in 1989 because the theory is based on electron-hole asymmetry, that the tunneling should be symmetric. That was done in 1989 because of a very fundamental property of the model. 9 years later or so, it was found that in all the cuprates, there is this asymmetry. Unfortunately, it's of the opposite sign because they choose to plot the voltage of the sample, and we unfortunately plotted the voltage of the tip, so it's the other way around. But it's the microscopic physics of these Hall superconductors is modeled by this correlated hopping Hamiltonian. One thing very important leads to is negative charge expulsion from the interior to the surface of the material. And that I claim is crucial because this negative charge expulsion is a very natural explanation of the Meissner effect that all superconductors exhibit. And I just want to tell you very qualitatively why that is. Meissner effect is expulsion of magnetic field from the interior of a superconductor, a normal metal when you pull. If you have charge that is out of the interior towards the surface in the presence of a magnetic field, the Lorentz force will deflect it so that it flows in exactly the direction that you need to create the current that will nullify the magnetic field. Here, let me go a little more detail. You will tell me BCS theory explains the Meissner, so let me tell you why it doesn't. So this is the initial normal metal in a magnetic field. This is the final state where the system is superconducting and magnetic field was expelled. There is a current here on the surface. The electron moves this way. For conservation of momentum, the body is rotating in the opposite direction. The way this happens is you need to expel the magnetic field gradually. So here is an intermediate step. As you are expelling the magnetic field, there is a Faraday electric field that is going this way, that is trying to prevent the expulsion. And this Faraday field is pushing negative electrons to move this way, and the positive ions of the body to move this way. And this happens throughout the transition. And yet you're supposed to believe that at the end, well, at the end, you know that this is the final state. The electron is moving exactly in the opposite direction as the Faraday field told it to do, and the ion is also moving in exactly the opposite direction. And so BCS doesn't address the process. BCS only looks at the energy of the initial and the final state. And the problem is that BCS cannot explain the process, while what I'm telling you is this expulsion of electrons in a magnetic field through the Lorentz force can explain the process by which you get the current near the surface. And there is also backflow of electrons that will explain how the body starts to rotate. And the fact that the transition is reversible requires that these normal electrons that are backflowing have negative effective mass, and that's a story I don't have time to tell you. but it's all. And here's some other qualitative pictures why I think it's very compelling. In plasmas, you have that. This is from a magnetohydrodynamics book. When you have a jet of conducting fluid, it bends the magnetic field lines. So if I just copy this and paste it the other way around, this is actually what happens in the Meissner effect. There is a flow of fluid out, which expels the magnetic field. Now the fluid has to carry 0 charge and 0 mass. In a solid, you can do that because it's electrons and holes, which carry 0 charge and 0 mass. So this phenomenology explains the Meissner effect. All right, so back to the mind. This is a summary of what I've been telling you. The canary was Ranga Dias. The current consensus that hydrides give ITC because of strong electron-phonon interaction. I believe there are many, many reasons to believe that Ranga Dias claims of room temperature superconductivity are false. If the resistance drops in Dias lab do not signal superconductivity, and all the other reasons I gave you, I think it's possible that the resistance in hydrides drops for other reasons. If the hydrides are not superconducting, I claim that there is no reason to believe that for other materials with heavier mass and weaker electron-phonon interactions, you will get superconductivity from electron-phonon. If so, there would be no electron-phonon superconductors. I presented you with an alternative possibility, the theory of cold superconductivity, very briefly. And within this theory, you don't want light ionic mass, you want materials that have hole carriers and negatively charged anions to get high TC, and pressure can help in this way. All right, thank you very much for your attention.
Okay, we have questions now. In the reflection of the paper that you can see that the TRL is
yes.
They explain in detail that while looking at the last after Eremets, they find that actually there was a freezing kind of point that was the blocking.
There was what? Yes.
So you're saying that maybe there's an issue with the actual result, and that there could be something that
yes.
But typically not, then do you really think that can happen in the context in the other?
No. The freezing transition for Europium, that was at 2 Kelvin. No. That's a totally different reason. But all I'm saying is the same process where they just arrange the data so it looked like superconductivity and the reason was something else. But no, it's not the same. No.
You're saying that
I'm saying the isotope effect exists, and thank you for asking, but the isotope effect can be due to, okay, here are some examples of isotope. I didn't plan the question, okay? When you look at the elements, the isotope coefficient is all over the place. It's a paper from Phil Allen in 1988. Some of them happen to be close to 0.5, some are 0, some are negative. Uranium has a negative isotope coefficient. Lithium under pressure has an alpha that's bigger than 1, less than 1. The cuprates have an isotope effect. The pnictides have an isotope effect. Strontium titanate has a very weird isotope effect is all over the place. And it can be due to a lot of things. And in our model of whole superconductivity, there is also an isotope effect because different ionic mass will cause different what we call the correlated hopping interaction that will also change the TC. It doesn't mean that the mass, the vibration causes the TC. It just means the ions are coupled to the electrons. It doesn't mean it causes TC.